in States, where he took his PhD under the supervision of from Berger, and then he went to Harvard and as a postdoc until '94. Then came back to Greece, to Crete until '99. Then as a postdoc at Demokritos until 2002, when he got the permanent post at Ioannina, and he's with us as a professor. Leandros is going to talk about some recent developments in the field of cosmology that his work has made some great impact, if I may say. Okay, Leandro, the floor is yours.
Okay, thank you, Sagi. It's a pleasure to have this opportunity to give this talk about the recent work that we are doing in our group. I should also say, first of all, Happy New Year to everybody. And I'd like also to thank Sakis for the organization of this very nice series of seminars in the context of our division, which is very helpful to not only present our work, but also to see various works from people relevant to this subject. Now, what I'm going to talk about, I should say first of all that as I'm doing with all my talks, I will be recording this seminar and upload this in the site of our groups. We have a site for our group, which is this one. If there is any objection in this recording, please let me know, and I can either stop it or edit that and remove some parts. Of course, it will be edited anyway, but is there any objection for that? I guess no. So I will just go ahead. So I will talk about today about a major tension in the standard model of cosmology, which is known as the Hubble tension. It has been persisting during the last several years, and it has been actually increasing in intensity. It's well known as the Hubble tension. And this tension has to do with the most basic parameter of cosmology, the Hubble constant, which is measured to be at very different levels between different measurements. And the question is, what could be happening there, and how can this tension at 5 sigma level be persisting for so many years? I will present an approach to this. Yes?
Sorry, can you upload it? Can you full screen the transparencies?
Okay, I have not. I thought I had full screen. Okay, I will just make it just, sorry, I will just change my desktop sharing. Do you see now my screen? Is it full screen now?
Yes, it's great.
Okay. So I will talk about an approach of this tension, which is based on an assumption of an ultra-late fundamental physics gravitational transition, which I'll try to discuss in the context of this talk. Okay, now you see the next transparency. Do you see the next transparency now?
Yeah, it's fine.
Okay. Now I will start by describing what is the Hubble tension and how is it related to the so-called M tension, where M is the absolute magnitude of supernovae, which is related to their luminosity. And I will say that these two are very much connected. Then I will discuss about the classes of models that have been designed to address the Hubble tension. And I will focus on particularly on the gravitational transition approach to address this problem. Then I will discuss about data and see how can one search. In fact, I will discuss a search for a signal in the data for this transition in the Cepheid star data. And I will argue that in fact there seems to be some signals for this type of effect there. And finally, I will conclude and discuss very briefly the existence of other datasets where one can search for such signals. Now let me start with describing the Hubble tension. Here you see the measurements of the Hubble constant according to a very wide range of methods. The most accurate method that we have currently to measure the Hubble constant is using the sound horizon as a standard ruler at the time of recombination. This is based on the cosmic microwave background power spectrum. And you see that we have very good measurements here, which is related to either the CMB or correspondingly the baryon acoustic oscillations which emerge from these sound horizon oscillations. So these are the best measurements we have currently. And the second best measurements are based on local measurements of the Hubble constant based on the supernovae, type 1a supernovae, calibrated using Cepheids stars as calibrators. Now this plot is from this recent review we wrote with a student of mine, Fotinis Kara, where we have a very extensive and detailed description of these types of tensions, and it's focusing mainly on the Hubble tension. Now the question is, why do we have this disagreement? What is the feature that distinguishes these two groups? You see they are grouped in roughly in two groups here. One group is here, and the other group is about 74 kilometers per second per megaparsec. Now, what distinguishes the two groups? Is it the fact that the CMB measurements are based on early time measurements based on the sound horizon and recombination, or is it that because we make an assumption that gravity is the same at all times from now until the time of recombination? Now, I will argue that this second approach has several advantages, and I will discuss about this. Now, let me review first of all the way that we actually go ahead to measure the Hubble constant. The most accurate and direct probes of the Hubble parameter and the Hubble expansion as a function of redshift generally is the measurement of distances. We have to measure distances, and from these of various objects at various redshifts, and from these distances we can infer the Hubble parameter and the Hubble expansion rate as a function of the redshift. And the most useful, the way to measure distances is to use either standard candles or standard rulers, that is objects that actually have known absolute luminosity, known power of radiation or objects that have a fixed size which we know. Now the most useful standard candles, that is objects whose luminosity is known, is the type 1a supernova, which emerges by starting from a white dwarf in the center here, and this white dwarf accretes matter from a companion supergiant, increases slowly its mass beyond its Chandrasekhar mass, and at that time it explodes and makes a huge explosion with luminosity equal to a galaxy about, and this explosion is known as type 1a supernova and occurs exactly when the mass crosses the Chandrasekhar mass limit. And because this mass is the same, or approximately, and the conditions are the same for all stars, the luminosity of these stars is approximately the same. So that's why they are called standard candles. The right name should be standardizable candles, because there are some other features that slightly change the luminosity, but we can calibrate these objects. For example, the metallicity, the structure of the white dwarf may change slightly the luminosity at the time of the explosion, but this can be calibrated using very simple empirical relations. So once we have the supernovae, which are seen at very high distances, we also have the gamma ray bursts, which can be seen at even higher redshifts, but these are not so easy to calibrate because they don't have such a simple mechanism, known mechanism, that we can actually calibrate and find their luminosity using empirical relations. So the basic idea is that we observe a standard candle, which could be either type 1a supernova, a gamma ray burst, or Cepheid star at very close distances or at high distance for the supernova. We measure the intensity of the radiation, this so-called apparent luminosity, this L. We assume that we know in some way the absolute luminosity, that is the power emitted, and then we can find, using this relation, the distance to this object using this relation. Now in a Euclidean space, the distance would be the usual distance that we know. In an expanding space, an expanding background like in a universe, this dl is connected with the Hubble expansion rate h of z using this equation here. So if we are able to know little l and large L for many objects, we are able to solve for DL and find this object. And if we do it for many objects, we know this integral for many objects, and then we can actually derive, using a fit, a chi-square fit, this h of z. Now, if we stick to very low redshifts, we can use an expansion here in this h of z and also find h naught by assuming not a cosmological model, a general parameterization, but a very linear expansion around z equal to 0. So that's more or less the name of the game that is being played for the local measurements of h naught. And the standard candles we use are the Cepheids stars, which are stars which oscillate, and their luminosity is connected with their period of oscillation, but we can observe them only at very low redshifts because they are not as luminous as the supernova. They are red giant stars. We observe them up to a redshift of about 0.01 from 0. Then we have the supernova, which are observed from 0.001 lower distances up to about 2.3 currently. And then there are the gamma ray bursts, which are less well calibrated. We don't know their standard, the absolute luminosity very well, and they go from 0.5 to about 6, to redshift 6. So these are the standard candles we have, and then what actually astronomers are using is not really the apparent and absolute luminosity, the power and the intensity of radiation. They use what they call magnitudes. They use the so-called apparent magnitude and the absolute magnitude of an object, which are connected with the corresponding apparent and absolute luminosities using this kind of relation. Of course.
What is this 0.5, 0.1? I think.
No, yeah, this is a typo. I want to mean 0.5 here. Okay.
So there is an overlap with the previous. Yeah?
There is an overlap. So that's the basic idea. You start with the Cepheids and then you make a ladder. You calibrate the next. You start with the Cepheids, which you calibrate using parallax methods, and then you know their luminosities. You know the distance, and from the distance you find the luminosity of Cepheids, of the very close by Cepheids. You calibrate them. Then you go to the next stage, etc., until you reach very high redshift. So it's like a ladder of. I will talk about this later. So the second way to measure the distances is using the angular diameter distance, which is based on standard rulers. And the typical standard ruler to use is the CMB sound horizon, which can be measured, which can be used to find distances, and it's depicted also in the CMB power spectrum and also in the baryon acoustic oscillations in large scale structure. So if we know the size of this object, let's say the sound horizon, and you measure the angle by which you see it in the sky, you can use this standard relation which connects the distance in a Euclidean space, for example, with the size of the object and the angle, and then you can find the distance. Now, in an expanding background, this distance is expressed again in terms of the Hubble parameter, the Hubble expansion rate as a function of the redshift, in this way. So if you can see the sound horizon effects on various redshifts up to the redshift of the combination, which is 1100, you can actually also in this way measure h of z, using now the sound horizon as a CMB sound horizon as a standard ruler. So these are the two approaches to obtain the Hubble expansion rate, and the strange thing is that for the h naught, these two give a very large disagreement. Now this is the baryon acoustic oscillation measurements of the sound horizon. The CMB, that's the way to see the effects of the sound horizon at a redshift of order 1 or at a redshift about 1100. Now let's see how can we measure the H0 using the standard ruler in some more detail. We use the sound horizon at recombination as a standard ruler in somewhat early universe. So we have this kind of we see a standard ruler here. We have the angle theta s, which we measure, and we have the angular diameter distance in comoving coordinates, which is measured at z equal 1100. Now the idea is that we measure this angle. How do we measure this angle? We measure this angle using the CMB angular scale power spectrum. You see, if you change, for example, this theta by about 8%, you see how the peaks move. So if we actually know the locations of these peaks, of this spectrum, these so-called Doppler peaks, first, secondary, and etc., we can actually know theta s from the CMB power spectrum, but we can also measure theta s using the effects of the sound horizon on the large-scale structure at later redshifts through the correlation function of galaxies. You see a characteristic peak here at a particular distance, which is correspondingly how you would view the sound horizon through large-scale structure at lower redshift. So we can see the same ruler at not only at the redshift of 1100, which is shown here, but also at lower redshifts through the baryon acoustic oscillations. Now, so the basic idea is you measure theta s with these two methods, and then you have RS, the sound horizon scale, which you actually can calculate. And the way to calculate the sound horizon scale is to see how much distance, what's the distance that a sound wave would have traveled from the time of the Big Bang until the time of recombination of decoupling. And you have CS, the sound horizon speed, times dt over the scale factor, because you got the comoving distance. And this you can change coordinates and express this in terms of h, the Hubble expansion rate, before the time of recombination. This is the expansion before the time of recombination, which depends on the density of baryons before the time of recombination, the density of photons, and the density of cold dark matter before the time of recombination. Now, these are all very well measured and known because we know, for example, the temperature of the CMB today, so we can infer the density of photons before the recombination. We also have know the density of baryons using actually this spectrum, the angular power spectrum of the CMB, and also using nucleosynthesis measurements. And also we know the ROS-CDM, the density of cold dark matter, also from various ways, including, for example, the CMB angular power spectrum. So it's a very well constrained quantity, this RS, to where it's very clear how to calculate this, and it's constrained by various observations. So now we go to this relation between theta s and RS, dA of z in the angular diameter distance, and we put here the RS, which we'll calculate from here, which is this value. We measure theta s, and dA of z, the angular diameter distance, we can express this in this form. We take h0 of z, which would be here, we take it out and we put in the denominator over here, and we write, and this E of z is now the Hubble free expansion rate, which in the context of lambda CDM is of this form. So we have only one parameter here, omega 0 matter, the density of matter, of cold dark matter, relative density with respect to the critical density. And you see that now this E of z here is very well constrained, because we have lots of standard rulers, standard candles, the baryon acoustic oscillations. We know this E of z very well after the time of recombination, because this here integral is after the time of recombination, from the present time until recombination. This is very well constrained. Now, so we also know RS here, and we can go ahead and infer the value of H naught, because this is measured, this is calculated, this is also measured very well, and from all these constraints we can actually infer the value of H naught. And the value of H naught that we find using this method is in fact lower than expected from local measurements. So the key point to notice is that there is a degeneracy between RS, between E of z and H naught. In other words, if you want to make this H naught bigger to be consistent with local measurements, you can actually change RS, try to change RS and make this smaller so that the product remains the same. And the way to make RS smaller is to change, for example, what you have here in this H of A, which appears in this integral. You can, for example, put in here, in addition to rho B, rho gamma, and rho CDM, you can put dark energy, another ingredient, rho dark energy, and this is called early dark energy, so that you decrease RS and therefore you increase H naught predicted by the CMB, and you make it consistent with the local measurements. Now, this is very dangerous if you do that, however, because you have to, whatever changes you make here, they have to disappear immediately after the recombination, because after recombination, everything is very, very much constrained in the Hubble flow. So if you put in dark energy, you have to make it disappear completely after recombination. That's a very fine-tuned process. All the models put in other things, like put additional radiation, neutrinos here, you can put additional dark energy. They have to make it disappear after recombination. That's a very fine-tuned process, and all these models suffer from this type of fine-tuning. And so these so-called early time models should be treated with care in general, and they actually have, it's known that they have this problem. Now, the other approach is the approach for the local measurements, which is based on yes.
What sort of fine-tuning we are talking about here? So 1 per 100?
For example, you have to use a very peculiar potential, for example, for the scalar. If you put the dark energy here in terms of a scalar field, you have to use a potential which is of the form, has a cos h to some power cos h phi to some power larger than 1, so 3 or something like that. Or cosine, sorry, cosine phi or something like that. It's a very tuned potential because you want to make it flat, you want to make it not oscillate very much, so it cannot mimic matter. And anyway, it has some problems, this kind of approach. It's a fine-tuning of the parameters of the potential that you have to use for dark energy.
Does inflation play some role, some models?
Inflation?
Yeah, because you mentioned potential, so
yeah, of course. I mean, one can connect this with inflation somehow as a second stage process. In fact, there are lots of people recently. The hottest model of early dark energy recently is the so-called new early dark energy, and this is based on a first-order phase transition. So you have two minima here. You have a minimum of a field, and then you have another minimum here. So the field is trapped here initially. It plays the role of early dark energy while it's trapped here, and then it immediately and abruptly goes down to this much lower minimum, to the lower minimum of the present day cosmological constant. And so because this happens abruptly, this transition, it has better features. So the best model the people have for early time model right now, the less fine-tuned, is this type of transition, which is also, however, it has the advantage it happens very abruptly, and then it stops here.
It's like this thin wall approximation.
Yeah, something like that. You have a thin wall approximation, and you actually make it's like the false vacuum decay of the Coleman in the early. So these are reviving now because you want something very abrupt to happen. And these models, the false vacuum decay approaches, seem to now be reviving because they can easily produce abrupt things happening. And this is what I'm going to also talk in the context of the late gravitational transition. It could also be used in the context of a late gravitational transition because there you also need something abrupt to happen. And these kinds of approaches are I think, seem to be part of the solution of this problem, either at early times before recombination, or as I will argue at late times, at ultra-late times recently.
Andre, if I may, something else. Actually, I had the same question with Yorgos about the inflation, and I totally understand how. I mean, you consider an early phase of inflation, which at some point has to end. So there is a transition period, the abrupt, as you said. But in terms of mathematics, more or less, when you calculating the sound horizon from this integral that you have here in the transparency, the fact that the scale factor changes over many orders of magnitude, if you assume a period of inflation, doesn't this make any difference? I mean, here when you integrate from zero, from Big Bang until the recombination time, the change in the scale factor, if you admit that there is a period of inflation, changes by many orders of magnitude.
Okay, yeah.
If you don't do that, then of course it is a much more usual, ordinary expansion up to the point of the recombination. In terms of rho, I understand that at some point the inflaton might decay and you end up again with the baryons, gamma, and CDM. But what about the evolution itself of the scale factor? That must have been dramatic changes if you have inflations at some period in between.
Okay, yeah, that's a good point, and I want to stress this is one of the reasons of the fine-tuning here, because you don't want to have inflation. You want to have a dark energy accelerating expansion. It doesn't dominate the expansion, it just increases h of A slightly by about 10% just before recombination, so that this RS decreases by about 10%. So you don't want to, so this should be an event that could happen just before recombination. Much before recombination, everything is the same, because you have nucleosynthesis. You cannot mess with nucleosynthesis, of course. So you want to have everything happening well just before recombination. Now this false vacuum here starts to have significant contribution to H. At that time, it actually has it accelerates the expansion slightly. It's not inflation, and then it disappears immediately because it goes to the true vacuum here. So that's the point of that's the reason of the fine tuning. It's because you want to slightly dominate, slightly accelerate H, and then disappear. But it's not inflation. Is it clear or?
Yes, thank you.
Okay. So let's go now to the second part, to the other approach. It's based on using Cepheids as calibrators. Now for Cepheids, we can measure their distance using parallax methods. So we can have this relation L equals L capital over 4 pi dl square. At small distances, we can actually measure dl using parallax methods, for example. We can measure also the L, the intensity of radiation, and we can infer their luminosity, for example, in the Milky Way or in the very close black galaxy in the LMC. We can infer their luminosity, and we can correlate this with their period. And then we construct a very clear empirical law which says that the luminosity magnitude is proportional to the logarithm of the period in days, and that's way we find an empirical way to calibrate the Cepheids using parallax methods. And then you assume that the same Cepheids exist also in further away galaxies where there are supernovas, because in very close by, in our galaxy and also in the close by galaxies there are no supernovas. But in further away galaxies, if there were supernovas, we would be dead. Our planet would have destroyed by the supernova effect because they are extremely powerful. Now, if now we can find supernovas at further galaxies away, and then we can actually use this as a ladder. So we first calibrate Cepheid stars locally using, for example, as you see here, parallax methods. Like here, this is a parallax method, and then you see the same, or assume that they are the same Cepheids at nearby galaxies, where you calibrate then the supernova. You find the absolute luminosity of supernova, at least you find how it depends on their properties, and then after you calibrate the supernova, and you fix their absolute luminosity, you go to even further, more distant galaxies, and you find the Hubble diagram in terms of find the Hubble parameter or the Hubble expansion rate using this calibrated supernova at more distant galaxies. This is called the distance ladder approach, and let's see it in some more detail. You start by fitting the supernova at low redshift to find the Hubble parameter, z less than 0.1. You use this equation between the apparent magnitude, the absolute magnitude, and the luminosity distance. Here you put megaparsec, that's why you have this 25 factor here. Now this equation is basically the same as this luminosity equation I wrote in the beginning. It's just expressed in terms of the magnitudes. And then you express the luminosity distance in terms of the integral of the Hubble parameter. You define the Hubble free luminosity distance, which has multiplication with h naught of dl, because then this cancels out the h naught from here, so it's Hubble free. It's independent of the Hubble parameter, this dl here, capital DL. And you write the theoretically expected apparent magnitude in terms of the absolute magnitude of the supernovae the logarithm of the Hubble free luminosity distance. The Hubble parameter also enters here, and we have also this unit for the 25. Now this may also be written in this way, who have the luminosity distance Hubble free, and then you have a constant calligraphic m, which is a combination of h naught and the absolute magnitude. So you see there is a degeneracy here again between the Hubble parameter as measured using in this approach and the absolute magnitude of the supernova. There is a degeneracy here also. And the way to proceed here is the following. You measure this quantity from supernova, you just observe them, measure their intensity. This is the apparent magnitude. You measure this absolute magnitude of the supernova using the Cepheids, this ladder approach, distance ladder approach I mentioned before, using Cepheids at z less than 0.01, below the Hubble flow. The Hubble flow starts, Hubble expansion starts at z larger than 0.01. And then once you have these measurements, you fit the Hubble free expansion, Hubble free luminosity distance using an expansion of the Hubble parameter at low z of this form. You see this deceleration parameter appearing here, and at the same time you fit h naught. So this is the name of, this is the way you do this using the local measurements, distance ladder approach. And you see it's crucial here that you have measured correctly this value of m using the Cepheids, and that the same value of m persists also, of course, at larger distances in the Hubble flow. That's a crucial observation. And another observation is that there is a degeneracy between m and the Hubble parameter, because what you actually measure is this combination, the calligraphic m gives the supernova. And then if you have Cepheids, you break this degeneracy by knowing m, and then you infer h naught. And another observation, there is no E of z dependence. There is no, like, it doesn't depend on the assumption of lambda CDM, because here at such low redshift, a cosmographic expansion is enough, is always good to describe the expansion rate. So we have a degeneracy here between m and h naught. Now if you want to also fit h of z at higher redshifts, the expansion rate, then you use supernovae at higher redshift at up to z max about equal to 2, which is much bigger than 0.1, which you use for the Hubble parameter. And you parameterize h of z, for example, using lambda CDM, you use this kind of parameterization. You put it into dl of z in this Hubble free luminosity distance, here in the denominator, and you have one parameter omega 0 matter, as opposed to h naught here. And you actually minimize chi-square in terms now of calligraphic m and omega 0 matter. So you have two parameters now to vary. Of course, h naught doesn't appear here because you don't care about h naught in this case. You care about omega 0 matter and calligraphic m. Actually, you only care about omega 0 matter. This is usually assumed to be a nuisance parameter. Most people marginalize over it, but even though I think it's not perhaps the best way to do that, but most people marginalize over it. And this way you find the best fit value of omega 0 matter. And of course, this is an independent this is a cosmological approach. But this is not what you do for the h naught. For h naught, you need the low z data, and you use this approach. And of course, the Cepheid measurement of m. So this is the name of the game. How does this tension now appear? If you start from the CMB approach with this relation I showed before, this theta s, you assume lambda CDM for E of z, the best fit lambda CDM, and you also assume standard expansion for RS, to evaluate RS, and then you evaluate H naught for Planck 18, as I call it, H0 Planck 18, which you find to be 67.36 plus or minus a very small error here, 0.54 kilometers per second per megaparsec, which you can then use into this calligraphic M parameter, which I showed in the supernova, which is measured from the supernova to be 23.8 plus or minus 0.01. And by knowing this and knowing also this value of m from the Cepheids, you can evaluate using this way the value of m for the Cepheids, because you know h naught, From here, you know M calligraphic, and you evaluate M from now, not from Cepheids, but from the CMB measurements. So it's a different way to find M in this way. And you find minus 19.401 plus or minus 0.027, which is actually smaller than the corresponding value of M that people find using the Cepheids. These are called R20. It's for RIS 2020. That's the measurement that they actually made for M. And so this is called the M tension, because you see, if you use the H node obtained from the CMB and you plug this into the calligraphic M expression for this parameter, you find a value of the supernova luminosity which is different, significant, about 4-5 sigma different with the new measurements from the value of M that you find with the Cepheids. And this is very closely connected to the Hubble-Tension because, of course, M and H node are degenerate through this measurable parameter calligraphic M. Now, how does this lead now to the Hubble-Tension? How does the M tension lead to the Hubble-Tension? Let's see that. You use again the calligraphic M parameter, which is measured in the Hubble flow for Z larger than 0.01, which is this value. You use the value of the absolute magnitude of supernova from the Cepheids, which is done at Z less than 0.01, very closer than the Hubble flow stars. And using these two measurements, you use now this correlation, and you infer H naught, since you know both M calligraphic and little m from the Cepheids, assuming that the M remains the same, the luminosity of supernova remains the same in the Hubble flow, Z larger than 0.01, and at distances closer than the Hubble flow where the Cepheids are seen. You make this important assumption, and using this assumption, you infer the Hubble parameter from local measurements, H naught for R20, RIS 20 is the measurement, and you find it's 73.2 plus or minus 1.3. Now this has gone to 1.0. It has been reduced based on a paper which just came out about three or four weeks ago by the SUSE team. And so this H0 obtained in this way is exactly 5 sigma away from the H naught obtained from the CMB. And so that's the Hubble tension, the H0 tension, which you see essentially emerges mostly from the M tension. It's very well connected with that. And so we have this degeneration, which this tension has been with us several years. It has been increasing in intensity. Now the observation to make here is that this the M parameter, the Hubble, the supernova absolute magnitude, which is the absolute luminosity essentially, depends on gravity, depends on the value of G effective, Newton's constant G. And so what is hidden here is the assumption that not only M is the same before and after the Hubble flow, but also it's the same, also that G effective is the same. That is essentially the gravity is the same before the Hubble flow starts and the same after the Hubble flow starts. So this is the key assumption here, which should be kept in mind. So it's in the roots of this, in our opinion, the roots of the Hubble tension. Now the hypothesis that we have introduced recently is that in fact all these problems would be resolved if we assume that the absolute magnitude of supernova is not the same before the Hubble flow start, that is before at Z less than 0.01, compared to Z after Z 0.01. Because what there is tal assumption make is that this measured value of M is the same before Z 0.01 and after Z 0.01. Then the tension emerges because the CMB M is of course very different compared to the local measurement M. But what all these things can be resolved is that if we assume that there is a transition in M induced, for example, due to gravity transition, and then MB, the MB is the absolute magnitude of supernova, changes close by or a little bit before the time of when the Hubble flow starts. And here you see the absolute magnitude of supernovae obtained by the measured apparent magnitudes and by assuming that the Hubble constant is the same as the CMB Hubble constant, which is the inverse distance ladder calibration of supernova, calibrated from the sound horizon. So this tension between this part and this part would be resolved if there was a transition at this time. And this is the M transition hypothesis, which could be induced by a fundamental physics transition which induces a transition of M at some redshift less than or about equal Z0.01. This was introduced for the first time in this paper that we wrote about a year ago with my students George Alessas and Laurentius Lavredis. And also it was further elaborated as a pure transition because here it was combined with a W transition. As a pure M transition was further elaborated in this paper that we wrote with Valerio Mara also about a year ago. Now, this type of transition would resolve the M tension, of course the Hubble tension because these two are connected, but could also potentially solve another tension which is known as the growth tension. According to this tension, the growth rate of perturbations that create galaxies and structure appears to be less strong, to be weaker than the growth rate that would be predicted based on general relativity and the CMB parameters that are obtained. So there are some indications for weaker growth than predicted in general relativity. And if we in fact connect this transition with a gravitational transition with a lower value of G, this could at the same time, as I will show later, address also the growth tension, because weaker gravity seems to be also required by completely independent cosmological data. Before we go to this part, let's see a little bit the approaches to the Hubble crisis. Here you see a plot of H of Z obtained from this paper here, the famous Planck 18 results paper. Here you see the Hubble expansion rate H of Z divided by 1 plus Z as obtained using the sound horizon calibration for the H node and in the context of lambda CDM, and you see that you have an expansion which ends up at about 67 kilometers per second per megaparsec. And then we have the Rees et al. Point, which is the about 74 kilometers per second per megaparsec, which is over there. And the question is, how can you make these two consistent? How can you make this local measurement point with this early time sound horizon calibrated point? Now, how do you make these two consistent is the basic question. How can you, and there are three approaches actually to do that. The first approach is to find some way to lower this point downwards, and this would happen either if there was systematics, major systematics in the analysis of Rees et al., which has to do perhaps with the way that Cepheids are treated, or if there was a transition. For example, even if there was a transition and in fact the true value of M in the Hubble flow is lower, then this would immediately bring this point down. So the transition that I described corresponds to bringing this point down. Alternatively, you could shift this whole line as is up, and at the same time as by changing the sound horizon, the calibrator, the real-time calibrator, for example, using early dark energy. And this would shift also the baryon acoustic oscillation points at the same time up, because they are also obtained from the same calibrator. So it would shift at the same time the points, these baryon acoustic oscillation points, and this line up. And this is the second. I should say that these points that I write here are not. There are many more points here. I just show here some of the points. This line is extremely well constrained by a very large number of baryon acoustic oscillation points, and also by supernova in this. So the shape of this line cannot be changed easily. That's the bottom line. But it can be shifted up as is, in the form it has. Now, the third approach is to actually try to deform this line, to say that in fact there is some kind of dynamical dark energy, and in fact we keep this integral consistent with the CMB sound horizon, but we deform this at late time so that it comes up and hits the value we want. Now, this approach has problems. First of all, it's very difficult to deform this line because you screw up all this data here. These data are extremely constrained, not these that I'm showing here, but other data which I'm not showing, which constrain this line very, very heavily from any deformation. Now I write the baryon acoustic oscillation data here are constrained. Also, if you do that, you worsen the growth tension that I mentioned before. You make stronger the growth of perturbations, and also you worsen the M tension because this calligraphic M quantity that I showed before changes. If you deform this, changes slightly, but it does change, the best fit from the supernova, in a way that also worsens the M tension. And in fact, the later you make the deformation, if for example you keep it like that and you shift it, let's say here, at very late times, then you completely screw up the M tension, you make it much worse. Even though it seems that you solve the H0 tension, because you change this calligraphic M quantity, you completely screw up the M tension. So these are the three approaches, and these are described in this paper that we very clearly in this paper that we recently wrote with George Alestas. So the question is, how do we? One approach, therefore, to actually so these two approaches seem to be more promising, and both of them work well if you have some abrupt event happening, either at late times or at early times. Now let's look at the gravitational transition and see how would this work if this M transition goes due to the gravitational transition, how would this work? And let's assume that the absolute luminosity of supernova is proportional to the Newton's constant to some power b. In that case, this change of m, because we want a change of m of about 0.2, you want 0.2 to be here, the change of m, would be induced by it corresponds to the change of luminosity of this form. And if you plug in this equation here, you find that delta m is equal to minus b times 5 half times the logarithm of me, which means the change of the Newton's constant before and after the transition. So G effective is the new Newton's constant after the transition. G Newton is the local value of the gravitational constant. And a natural value of this parameter b, this power b, is the value minus 3/2, because it's natural to assume that the absolute luminosity is proportional to the Chandrasekhar mass, the mass which induces the collapse and the explosion of the supernova. The more massive it is, the more luminous one would expect it will be. So in that case, the L would be proportional to the G to the minus 3/2. Of course, this is the simplest approach. One can also have different, more detailed studies of this power. But if it's minus 3/2, that is the simplest approach, then we have that delta m, the change of the absolute magnitude during the transition, is connected with 15/4 logarithm of the change of the Newton's constant, that the ratio of G after over G before. And it turns out that the required change of G is about 10% in this case, which could induce a delta m equal to 0.2, which is needed. So you need weaker gravity at early times by about 10% to induce this delta m equal to 0.2. And this weaker gravity would also solve the growth tension, because here you see a plot of the growth tension. Here are the contours. These are the two parameters sigma 8 and omega 0 matter, which are measured either through the CMB or through these red contours, or through directly the peculiar velocities of growing structures through this kind of data, redshift space distortion data as they call. And you have the direct measurements of growth, which are the blue contours, and the indirect measurements through the CMB, which are the red contours, you see there is some tension about 2 to 3 sigma between the direct growth measurements and the CMB, and you see that the CMB predicts a higher value of sigma 8 is the amplitude of the power spectrum of the fluctuations, so it's the amplitude of primordial fluctuations. Now, if on the other hand you allow for weaker gravity for this transition, then you increase the sigma 8, the amplitude of the primordial fluctuations, to a value which becomes consistent with the Planck value. So the growth tension, it becomes practically disappears. While on the other hand, if you actually try to deform the Hubble parameter, the h of z, this tension increases. If you put an h of z which is deformed so that actually you can solve the Hubble tension using deformation of h of z, you have worsening of growth tension. So a different, if you want, byproduct of this approach is to ameliorate, to smoothen, to reduce or to make it disappear the growth tension due to this effect. This plot is in this paper with Valerio Mara, which if one wants to actually look at this. So the main question that exists right now are the following. Is such a transition consistent with current constraints on G effective? How consistent on general relativity? The answer is yes, because even though this seems to be a large change, the local constraints on the variation of G only constrain the time derivative, the local time derivative. So in the context of a transition, the time derivative is 0 here, and it's also 0 here. It's only at a particular point which changes abruptly. So it's not easy to catch it with measurements which only measure the time derivative of G effective, because the solar system, for example, in this region would be consistent with this a fixed value of G. It would be very hard to detect the transition using solar system, for example, measurements. The second question is, are there hints for such a transition, for such gravitational fundamental physics transition in astrophysical data on scales less than 40 megaparsecs, ZT less than 0.01? Now, in fact, it would be very surprising that people would have missed this transition. In fact, it turns out, according to the studies we have tried, the research we have made, that this is very, very hard to actually detect if it's really a transition. In fact, not only is it hard to detect, but also there are some hints at 2 sigma levels in the Cepheids data, in Tully-Fisher data, and also in solar system history data. In fact, there are some papers which argue that the number of impactors on the Earth and Moon system has increased by a factor 2 to 3 about 100 million years ago. So it could, so this is a big puzzle in the solar system history, and people have tried to solve this using various ways. In fact, this is also connected to the disappearance of dinosaurs, because the dinosaurs disappeared through an impactor, most probably. And this is a very major question. What was the origin of this impactor? Why did it happen at this particular time? And what was the origin of this increase of impactors? So in the context of these transitions, we have actually a paper which is on its way. One can actually explain this increase of impactors if this transition of G had happened in the solar system. We also have found hints of such a transition in Tully-Fisher data, which is an empirical relation which connects the velocity with the rotation velocity with the mass of various galaxies. And we find some change in this data which has occurred roughly at the time that we would expect it. And also we recently found some similar effects in the Cepheids data, which appears to happen at about 20 megaparsec away in this paper, which was published very recently. And also in this paper we also found these hints in the Tully-Fisher data. If I have some more time, I will try to describe this Cepheids paper, because I don't have time to describe all of this. And the third question is, are there theoretical models that naturally and generically predict this type of transition? And as I said before, indeed, a false vacuum decay of a scalar field which is non-minimally coupled, for example, a chameleon or a symmetron field, could indeed generically induce through a first-order phase transition this type of change. So this is a simple and generic mechanism which could induce this type of effect. Now let me say a few things in the remaining time about the Cepheids. What is the signal we found in the Cepheids? Because I don't have time to talk about the Thule Fisher or the solar system data.
Leandre, we have to go a bit quick because we are on time, slightly over time.
I will, 5 minutes more, I will finish. So now we have this type of approach for the Cepheid. This is the apparent magnitude of the Cepheids. This is the jth Cepheid in the ith galaxy. We have this apparent magnitude. This is a color relation. This is the magnitude of the different colors. This is the distance modulus. This is the distance to the Cepheid. This is the absolute magnitude of the Cepheid, and these are the calibrator parameters. This is the period of the Cepheid, which connect the luminosity, the apparent magnitude, with the period, and this is the metallicity, and this is a parameter which connects the Cepheids which also calibrates the magnitude. Anyway, I will not say any more because I don't have much time. And these are all the corresponding supernovae in the host galaxies of these Cepheids. Now we have about 2,000 to 3,000 data for the Cepheids. So we have these parameters to fit. These are the output, the parameters to fit. This is the distance to the Cepheid, the absolute magnitude, these parameters here, and the magnitude of the supernova in the hosts of Cepheids, the host galaxies. And the input are the data, these colors, the periods of the Cepheids, the metallicity of the Cepheids, etc. So we play this game, and we use, these are the input, the data, and these are the parameters to fit. We connect this using this relation, which is essentially a matrix relation based on this equation here. We minimize chi-square, and what people do is you find these parameters Rw, etc., and you find this MB, this absolute magnitude of supernova here, which is the value that people find this is the minus 19.244 I said before. This is how it's obtained by using this type of fit. Now, a key assumption here is that one assumes a single value for this parameter. This Rw is assumed to be a universal parameter, and also universal is this MW, and all that is assumed to be the same for all Cepheids. What would happen, however, if we change this and allow for two universal parameters, M for close by Cepheids and another M absolute magnitude for further away Cepheids? Then the analysis is the same roughly, but with one more parameter. Or we can play the same game with the R. We can allow two types of R, this parameter which appears here. In other words, what would happen if we allow more parameters here, allowing for a transition? Anyway, I will just skip this. What happens is that in fact a transition is favored by the data at about 20 megaparsecs to be happening. And not only it's favored by the data, but if you allow for this, you change the value of best fit value of M for the supernova from minus 19.25, it goes to minus 19.36, which is much closer to the value of M obtained from the CMB, and also the value of H0 becomes very much consistent with the value of the CMB sound horizon value. So if you allow for a transition, the data want to take it, and they take the transition, and once they take it, they change their value, they take the parameter values to values which are naturally consistent with the microwave background, with the CMB sound horizon value. And we thought that this was a very interesting effect, which came after we proposed the model. And so even if we use model selection criteria, even though you have one more parameter, this is favored using model selection criteria. We have used various types of increase of parameters. You see these are the model selection criteria. these are the corresponding models where we only have put two parameters more, that is allowing for a transition. And you see that the AIC and BIC criteria favor, the Bayesian information criteria favor this type of models. If, of course, we allow all galaxies to have their own parameter values, RW or MW, we find that the selection, because we put too many parameters, then it's not favored by the model selection criteria. This is the Bayesian criterion, but that's because we've put in there too many parameters. But if you put only two parameters, it's in fact favored by this selection criteria. So now this, you see that the various models we used by increasing the number of parameters, all these are this is the M versus the probability here. You see that if this is the base SUS, the original analysis made by the SUS team, which gives this tension, this M tension. But if we allow at least one more parameter, then you see how these curves shift and become consistent with the CMB value. And of course, since the M and H naught tension are related, the same happens also for the H naught case. For the H naught, you see that as soon as we allow various models with increased, which allow the transition, then all these curves move from the tension range, they move to the range of the CMB. So anyway, this now we have the new SUS analysis. Even in the new, we have talked with the SUS members, Rees et al. We had long exchange of emails about this situation. They argue that perhaps we have underestimated the errors in our analysis. But when I saw their new paper, in fact, this is the new paper that just published a month ago, they themselves seem to actually see the same effect, even though they don't admit it. If you see, this is the BW parameter from the Cepheids, and you can see these are the close by, this is not distance actually, but it's close to being distance. And you see that the anchor galaxies, the close by galaxies here, which are used as anchors for this Cepheid, on the average have a different value of parameter of BW. This is the period luminosity B parameter I showed before as BW, compared to the other galaxies which are host galaxies further away. And in fact, their own papers, they claim that everything is consistent with the blue line, but it's apparent that it's not consistent. All these data points are above the blue line. In fact, we did an analysis of their data using plot digitizer to analyze this, and we found that in fact, if we bin the data to low and high distance, the two bins differ by up to 4 sigma, depending if you take the outliers in or not. And this is the critical distance where we divide this dataset in two parts. And you see, if you divide, let's say, about 30 megaparsec, the bin which is below 30 megaparsec is significantly different from the bin at 100 megaparsec. That's their own data, their own analysis used in their paper. So anyway, this is now what's the theoretical model? Now I will just skip this. I said already before, this would be a Lagrangian for a modified for scalar tension theory, which would have a transition from a false vacuum to a true vacuum. And in fact, people have done evaluated the scale of these bubbles in the context of various models. This paper has this calculation, and the scale of the bubbles, if you put Tc here, the present temperature of the CMB, you find that these bubbles, and if you also put the scale of the cosmological constant for the false vacuum, you put the lambda here, you find that the size of these bubbles comes out to about 15 megaparsecs due to this logarithmic dependence here on the size of the bubbles. So if this analysis is true, then a natural size of these bubbles would be 1/300 of the current horizon Hubble scale, which is about 15 megaparsecs. So this is with Nick Maragakis, my student in progress, to go deeper into this part. I will stop here. These are the conclusions. Thank you for your attention. I would be glad to answer any questions if you have any.
Thank you very much, Leandro, for this very nice talk, informative talk. Questions, please?
Could I ask a question?
Yes.
Leonard, thank you very much for this very beautiful talk, very informative. I was just wondering, you're definitely the expert in variable G models in cosmology. I was impressed by the fact that we only have local time derivative constraints on G effective. That means that we can allow for different values of G effective over different periods of the universe, different time periods in the evolution of the universe without actually having any very rigid constraints, any big difference in the type of evolution that we see nowadays?
Okay, that's a good question. Here you see a plot which I had prepared to show, but I didn't have time to show. These are the constraints on G, on the derivative of G, using various kinds of probes. This is from this paper with George Alessas and Yannis Antoniou, which we had a few months ago. And you see here that G dot over G is constrained by various objects. Now, for example, from local solar system, a constraint, lunar raising, and pulsar timing, and you see that all these are local constraints on G dot over G at particular times in the past. For example, this is at the present time, solar system, but this is strong, this pulsar timing is somewhat earlier in the past, but it's again local, using a particular time, the time that we observe it. Now, of course, there are also constraints on delta G over G, which, however, are about close to 0.1. The best is about 0.1 or at most 0.05 if you combine the nucleosynthesis with the Big Bang constraints. So you see the delta G over G is much more weak constraint than G dot over G. That's what I meant. I didn't mean that, in fact, and G dot over G, of course, at various times, not only at the present time. For example, these globular clusters correspond to a different time in the past, which corresponds to much higher distances. But they are all at a particular instant in time. All time, but an instant. The time that we actually observe this kind of evolving system. Delta G is much weaker constraint. You see, goes from 10 to the minus 13, goes to 0.1 or 0.05. So that's what I meant by saying that the constraints are much weaker for the difference of G compared to the time derivative.
Okay, thank you very much.
Any other questions? Okay, since there's none. Okay, thank you very much, Leandro, for this very nice talk. We will take a